Hello everyone, welcome to the video lecture of this course Heat Transfer. So today we will start one new module that is known as boiling and condensation. So as we have studied in thermodynamics that these boiling and condensation concepts, these are just opposite to each other. Like boiling, it is the phase change from the liquid to vapor state, but this condensation, it is actually the phase change from the vapor to the liquid phase. Now, today we will discuss this boiling heat transfer in details. So, there we will study the different types of boiling heat transfer like the pool boiling, then forced convection boiling, which is also known as flow boiling, then subcooled boiling, saturated boiling. All these four different types of boiling phenomena we will study in details. After that, we will study the boiling regimes, that is the flow curve of water. In case of the boiling, we will study, and then the film boiling, nucleate boiling, all these things regarding this flow boiling regime and this flow curve, we will study in details. So let us start this lecture. So what is the difference in between the evaporation and boiling? So the evaporation, it actually occurs at the liquid vapor interface when the vapor pressure is less than the saturation pressure of the liquid at a given temperature. In this diagram we can see that the evaporation, it is occurring at the liquid vapor interface, but the boiling, it is the phase change which occurs at the solid liquid interface when a liquid is brought into contact with a surface maintained at a temperature sufficiently above the saturation temperature of the liquid. So in this diagram we can see that at the bottom of this container the water started boiling. That container, that bottommost surface, its temperature is higher than the saturation temperature of the liquid, and in this solid liquid interface the boiling occurs, it started. So this is the difference in between the concept of evaporation and boiling, that evaporation occurs at the liquid vapor interface, but the boiling occurs at the solid liquid interface. So boiling, it is actually a convective heat transfer process which involves a phase change from the liquid to the vapor state. So it is also defined as an evaporation at the solid liquid surface. So here we have seen that evaporation is actually occurring at the liquid vapor interface, but boiling can also be defined as an evaporation which is occurring at the solid liquid interface. So this is actually possible when the temperature of the surface, it exceeds the saturation temperature corresponding to the liquid pressure. Now the heat which is transferred from the solid surface to the liquid, in case of this boiling, it obeys this formula, that is Q equals to HAS into Ts minus T saturated. So this Ts minus T saturated can be represented as delta TE. So this delta TE, this is actually Ts minus surface temperature minus saturated temperature, and it is known as the excess temperature. So there are some application of the boiling heat transfer like the steam production in steam or nuclear power plant, then the heat absorption in refrigeration and air conditioning system, then the cooling the machines like nuclear reactor and rocket motors. The large quantities of heat are released in relatively small volume. So these are some application of the boiling heat transfer. Next we will discuss the classification of the boiling. So there are actually four different kinds of boiling heat transfer phenomena. First is the pool boiling. So this boiling, it is called pool boiling in the absence of bulk fluid flow. So what happens here, any motion of the fluid, is due to the natural convection currents and the motion of the bubbles under the influence of buoyancy. The concept of buoyancy we have already studied in fluid mechanics part. So in case of this pool boiling, any motion of the fluid, it is due to the natural convection currents and the motion of the bubbles under the influence of buoyancy. So in case of this pool boiling, the liquid above the hot surface, it is essentially stagnant, and its motion near the surface, it is due to the free convection and mixing induced by bubble growth and the detachment. So this is the concept of this pool boiling. So this pool boiling, it occurs in steam boilers involving the natural convection. So here the absence of bulk fluid flow is there in case of this pool boiling, and it happens due to the natural convection current. The fluid motion happens due to the natural convection currents. Next, the flow boiling, or it is also known as the forced convection boiling. So what happens there? The boiling is called the flow boiling or forced convection boiling in the presence of the bulk fluid flow. So in this forced convection or flow boiling, the fluid is forced to move in a heated pipe or over a surface by external means such as a pump. So as the fluid is forced to move inside a heated pipe or over the surface by external means, so that's why the name is flow boiling or forced convection boiling. Here the liquid is pumped and forced to flow. So this type of forced convection boiling, it occurs in water tube boilers involving forced convection. Next, we are having the subcooled boiling. So when the temperature of the main body of the liquid is below the saturation temperature, then the subcooled boiling it occurs. So what happens in case of the subcooled, or it is also known as the local boiling. So in case of this local boiling, the liquid temperature, it is below the saturation temperature, and the bubbles are actually formed in the vicinity of the heated surface. So you can see here the bottom of the container, bubbles are being formed. Now these bubbles, after traveling a short path, they get condensed in the liquid which has a temperature less than the boiling point. Okay, so this is the concept of this local or subcooled boiling. Next we are having the saturated boiling. In case of this saturated boiling, the temperature of the liquid, it is equal to the saturation temperature. So in case of this saturated boiling, the liquid temperature, it exceeds the saturation temperature, or it is equal, or it may exceed the saturation temperature. The vapor bubbles, which you can see in this diagram, the vapor bubbles are formed. The vapor bubbles, they form at the solid surface, or you can see at the bottom of the container. At the liquid solid surface, the vapor bubbles are formed in case of this saturated boiling. And after forming of these vapor bubbles, they propel through the liquid by buoyancy effects. And after a certain amount of time, they escape from a free surface, that is the liquid vapor interface. Okay. So this is the concept of this saturated boiling. So these are the boiling phenomena in pool boiling, then forced convection or flow boiling, then subcooled boiling and saturated boiling. So these are the four different classification of boiling heat transfer. Now we will discuss the pool boiling with liquid vapor interface. So Actually, the boiling process depends upon the nature of the surface, then the thermophysical properties of the fluid, and the vapor bubble dynamics. So, the nature of the surface, then thermophysical properties of the fluid, and vapor bubble dynamics. So, these are the three important criteria upon which the boiling process depends. Now, due to the involvement of large number of variables, general equations describing the boiling process, these are actually not available. So, in this diagram of pool boiling, we can see that there are two different diagrams. So, one temperature distribution in saturated pool boiling with a liquid vapor interface. It is shown here. Now from the figure, we can see that there is a sharp decline in the liquid temperature close to the solid surface. So it is visible in the diagram, the right hand side here. So there is a sharp decline we can see in the liquid temperature close to the solid surface. Now the temperature through most of the liquid, it remains slightly above the saturation, because it is that graph, it did not touch the temperature surface. It is the excess temperature axis here. So consequently, the bubbles generated at liquid solid interface, they rises and are transported across the liquid vapor interface. So this bubble formation or the vapor bubbles which are formed at the liquid solid interface, we can see in the left hand side of this diagram. So this is the formation of pool boiling, but whether the boiling formation it corresponds to pool boiling or forced circulation or flow boiling, there are actually three definite regimes of boiling. Okay, so what are those three definite regimes? They are known as, number one is interface evaporation, then number two is nucleate boiling, and number three it is the film boiling. Now you can see in this diagram the boiling curve for water. So this specific boiling curve for water, it has been obtained from an electrically heated platinum wire submerged in a pool of water at saturation temperature by varying its surface temperature and measuring the surface heat flux. So in this way, this boiling curve for water, it has been achieved. So what we have done, an electrically heated platinum wire, it has been submerged in a pool of water at saturation temperature by varying its surface temperature, and then we have measured the surface heat flux. So that surface heat flux we can see in this diagram at the y-axis, that is Qs, watt per meter square. Now in this diagram we can see the three different or the definite boiling regimes. The number one, it is the interface evaporation or free convection. Then the nucleate boiling, it consists of the zone 2 and 3, and then the film boiling, which consists of the zone 4, 5 and 6 for this boiling curve. So let us first discuss the interface evaporation or the free convection. So what happens in case of this interface evaporation? So here the evaporation occurs with no bubble formation. So this interface evaporation, it exists in the region 1, which you can see in this diagram 9.2. So it is also known as the free convection zone. Now here the excess temperature delta E, that excess temperature, this is actually Ts minus T saturated, that is T surface minus T saturated. That excess temperature, it is very small and it is almost equal to 5 degrees centigrade. Okay, so the value of this excess temperature in case of this free convection or interface evaporation, it is very small and almost equal to 5 degrees centigrade. Now in this region, that is zone 1, the liquid near the surface, it is slightly superheated. Then the convection currents circulate the liquid and the evaporation takes place at the liquid surface. So this is the concept of this zone 1, that is the free convection zone or interface evaporation. So what happens there? The liquid near the solid surface, it is slightly superheated and the convection currents they circulate the liquid and the evaporation takes place at the liquid surface. And next we are having the zone 2 and 3, and which is under the nucleate boiling zone. So this nucleate boiling zone, it comprises of the zone 2 and 3. In this diagram you can see that with the increase in the excess temperature, that is delta TE, the formation of bubbles on the surface of the wire at certain localized spots commences. Okay. So this is the thing happens in case of this nucleate boiling, that is in the regions 2 and 3. Means when the excess temperature is increased, the bubbles are formed on the surface of the wire, and then the bubbles, what happens with these bubbles? The bubbles condense in the liquid without reaching the liquid surface. Okay. Now in the region 2 where the nucleate boiling starts, that we can see at the end of zone 1, that is at the end of free convection zone, the zone 2, here the bubbles condensing superheated liquid, that is in zone 2 the nucleate boiling it gets started. Now with further increase in delta T, that is the excess temperature, when the excess temperature is further increased, the bubbles are formed more rapidly and rise to the surface of the liquid, resulting in rapid evaporation. So which we can see in this diagram, zone 3, the bubbles rise to surface, it is written here. So the rapid evaporation occurs in this zone 3 under the nucleate boiling. So this nucleate boiling, it is characterized by the formation of bubbles at the nucleation sites and the resulting liquid agitation. Now this bubble agitation, it induces considerable fluid mixing, which promotes the substantial increase in the heat flux and the boiling heat transfer coefficient. So this is the concept of this nucleate boiling. In zone 2, the bubbles condensing superheated liquid, at the surface, the bubbles are formed on the surface of the wire. When the increase in the excess temperature, then the bubbles gets formed and these bubbles condense in the superheated liquid, which happens in the zone 2 in this diagram. And in this zone 2, the nucleate boiling it gets started. After that, in the zone 3, the bubbles rise to the surface, that means there the rapid evaporation it occurs in this zone 3. Next we are having the film boiling. So under this film boiling, you can see in this diagram there are 3 different zones, which are zone 4, 5 and 6. So which are actually here written this unstable film, stable film and radiation coming into play. Okay. Now when the nucleate boiling it ends after the zone 3, then in the zone 4 the film boiling gets started. So here we can see in this diagram of the boiling curve for water, a point A is given, which is at the end of the zone 3 and it is at the start of the zone 4. That means at the end of nucleate boiling and at the start of the film boiling. Okay. So the maximum heat flux, it is known as the critical heat flux. It occurs at this point A, and it is of the order of 1 megawatt per meter square. In case of this nucleate boiling, it exists up to the excess temperature of 50 degrees centigrade. In case of this first zone, that is the interface evaporation or free convection, we have seen that the excess temperature is very small, or this is almost equal to 5 degrees centigrade. But in case of this nucleate boiling, it exists up to the excess temperature of 50 degrees centigrade. And this point A, it is known as the critical heat flux. It is the maximum heat flux. So next, at the end of the zone 3, the zone 4 started, which is the film boiling, and under the film boiling and the zone 4, it is known as the unstable film. So this film boiling, it comprises of the zone or regions 4, 5 and 6. Now the trend of increase of heat flux with increase in excess temperature, it is observed actually up to region 3, where we have seen when the excess temperature is increasing in the x direction, the heat flux, it was also increasing up to point A, that is the maximum heat flux or the critical heat flux. So but in case of this zone 4, it actually gets reversed, that is when the excess temperature it is increasing, the heat flux it is decreasing. So this is actually due to the fact that the bubble formation it is very rapid, and the bubbles blanket the heating surface to prevent the incoming fresh liquid from taking their place. Okay, so that's why eventually the bubbles coalesce and form a vapor film which covers the surface completely. Since the thermal conductivity of vapor film is much less than that of the liquid, the heat flux actually drops here with the growth of the excess temperature. And that is why in case of this unstable film, the heat flux gets decreased with the increase of excess temperature. Because the bubbles, they form a vapor film here. Now within the temperature range of 50 degrees centigrade to 150 degrees centigrade for the excess temperature, these conditions oscillate between nucleate and film boiling, and this phase it is actually referred to as the transition boiling or partial film boiling or the unstable film boiling, which is denoted here as the unstable film under the film boiling. Now if the excess temperature is further increased, then the vapor film it is stabilized and the heating surface it is completely covered by a vapor blanket, and the heat flux it is as the lowest, which we can see in this zone 5 or region 5. Now the surface temperatures required to maintain a stable film, these are high, and under these conditions a sizable amount of heat is lost by the surface due to radiation, so which is indicated in this zone 6. So at zone 5 we can see that the heat flux it was the minimum, it was the lowest when the excess temperature is increased, but after that the heat flux again gets increased with the increase in the excess temperature. Now the phenomenon of stable film boiling can be observed when a drop of water falls on a red hot stove. So that drop actually does not evaporate immediately, but it dances a few times on the stove actually. So this is due to the formation of the stable steam film at the interface between the hot surface and the liquid droplet. So these are the concept of the three different regions or three different zones under the film boiling. Now there is one important terminology that is known as the critical heat flux or burnout point. This is actually that point A here in this diagram. So it is the point of maximum heat flux on the boiling curve at which the transition from nucleate to film boiling initiates. So in this diagram we can see that at this point A, the heat flux it is maximum, and the zone 3 of the nucleate boiling it gets ended in this point A, and from this point A again the film boiling it started. So this is like a transition zone in between the nucleate and film boiling. It is in between the zone 3 and zone 4. Now this point it is also known as the boiling crisis actually. So because the boiling process beyond this point is unstable unless the point B is reached in this diagram. That is in case of the zone 6. Now the temperature at point B it is extremely high and it is normally above the melting of the solid. So if the heating of the metallic surface is not limited to point A, then it is possible that the metal may get damaged or it may even melt. So, and for this reason the point A is termed as the boiling crisis or burnout point. Okay, so this is the concept of this critical heat flux or the burnout point. Now here in this diagram we can see that the methanol boiling on horizontal 9.53 mm diameter copper tube heated internally by condensing steam. So in this first diagram at temperature 37 degrees centigrade Q by A equals to 242.5 kilowatt per meter square, you can see that the nucleate boiling. So this is the actual diagram of the nucleate boiling that comprised actually of zone 3, zone 2 and zone 3. After that, in the second diagram, it is the diagram of the transition boiling. And lastly, when it gets stable, then we can see the third diagram. It is the diagram of the film boiling. So these are some real life snapshot of the boiling regimes, that is the nucleate boiling, transition boiling and the film boiling. Let us now discuss the bubble shape and size consideration. So here you can see that for the three different cases the typical shapes of the steam bubbles are given. In the first case it is totally weighted, in the second case it is partially weighted, and in the third case it is unweighted. So what happens and what influences such type of shape and size of the bubbles? The heat transfer rate in nucleate boiling it is greatly influenced by the nature and condition of the heating surface and surface tension at the liquid solid interface. So actually what happens, this boiling and condensation heat transfer, these are actually much more complex compared to the natural convection process. Actually they depend upon the latent heat effects, then the surface tension and the surface characteristics. So that is why this boiling heat transfer, these are much more complex compared to the natural convection process. Now the surface tension signifies the wetting capability of the surface with the liquid, and that influences the angle of contact between the bubble and the solid surface. Now if the surface is contaminated, its wetting characteristics are affected, which also influence the size and shape of the vapor bubbles. Now if the surface tension of the liquid is low, then it tends to wet the surface, because the surface tension it is actually the wetting capability of the surface with the liquid. That is what the low surface, if the surface tension is low, then the surface is highly wetted. Now if we consider that the surface tension of the liquid is low, then it tends to wet the surface so that the bubble is readily pushed by the liquid and it rises. Now the liquid shear of the bubbles causing them to become globular or oval shape. So which can be seen here in case of this number 1 diagram that is totally wetted. So here the surface tension of the liquid is low, that means the highly weighted surface, and that's why the shape of the bubble it is globular or oval shape for totally weighted surface. Now in case of liquids having intermediate surface tension, that means the partially weighted surface, in that case a momentary balance may exist between the bubbles and the solid surface, so that it is necessary to form larger bubbles before the buoyant force can free them from the surface. Now in case of this partially weighted surface, the shape and size of the bubble you can see here. And in case of the third part, that is in case of the unweighted surface, the bubbles actually spread out, forming a wedge between the water and the heating surface, and they allow the hydrostatic forces to resist the action of the buoyancy. So these are the theory for these totally weighted, partially weighted and unweighted surfaces where the bubble shapes and sizes varies with the surface tension characteristics. Let's discuss the bubble growth and collapse. So from different experiments, it has been observed that the bubbles are not always in thermodynamic equilibrium with surrounding liquid actually. Now the vapor inside the bubble, it is not necessarily at the same temperature as the liquid. So suppose in this diagram you can see the force balance on a spherical vapor bubble. It has considered different forces are acting on the spherical vapor bubble. The pressure forces on this bubble must be balanced by the surface tension at vapor liquid interface. So if it happens, then we can write that pi r square into PV minus PL, this is equals to 2 pi r into sigma. That sigma it is the surface tension. Now PV minus PL, this is equals to 2 sigma by r. So this PV it is the vapor pressure inside the bubble. PL it is the liquid pressure over the bubble surface, and sigma it is the surface tension of the vapor liquid interface. Now the vapor it may be considered as a perfect gas for which the Clapeyron equation may be used. Now what is this equation? This is equals to dP by P. This is hfg by RT square into dt. At this hfg it is the latent heat of vaporization. Now from the perfect gas law we can write that P by RT equals to rho V, where R is the gas or vapor constant and rho V is the density of the vapor formed. Now if we substitute this above equation in the earlier equation, that is the Clapeyron equation, then we will get that dP by dt this is equals to hfg into rho V divided by T. So that means we are getting PV minus PT divided by TV minus T saturated, this is equals to P HFG divided by R T saturated square. So here TV this is the vapor temperature inside the bubble, and T saturated this is the saturation temperature of vapor inside the bubble at PV. Now from these two different equations we are getting the difference in between the vapor temperature and the saturation temperature. This is equals to 2 sigma by R into R T saturated square divided by P HFG. So this equation it actually suggests that if TL minus T saturated this is greater than TV minus T saturated, in that case the bubble of radius R it will grow, and otherwise it gets collapse. Here TL it is the temperature surrounding the bubble. So this is the derivation of this bubble growth and collapse formation. Now let us discuss this boiling correlation. Earlier in case of convection heat transfer we have studied different correlation in terms of the Nusselt number. So in case of this boiling correlation, that is in case of this phase change from liquid to vapor, in boiling heat transfer a driving force is the excess temperature. So that excess temperature, it is actually known to us, which is delta T. It is T surface minus T saturated. And for the boiling process, the governing equation, it is Q equals to HA into delta TE, where H is the boiling film coefficient. So this is similar to the Newton's law of cooling that we have studied in the convection rate equation. So in the next class actually we will study some more correlations, that is the nucleate pool boiling, then in case of the critical heat flux, then film pool boiling. All these different correlations we will study in one of the next class, and based on those different correlations we will discuss different numericals. So today actually we have discussed the concept of the boiling heat transfer, the difference in between the boiling and condensation and boiling and evaporation. After that we have discussed the four different types of boiling heat transfer, which are pool boiling, then flow or forced convection boiling, then saturated and subcooled boiling. After that we have discussed the boiling regimes, and that there we have discussed the boiling curve for water, and there we have seen the 6 different regions or zone in case of the boiling curve for water. That curve was the heat flux versus the excess temperature. In there, 3 different zones were there, that were the interface evaporation, the nucleate boiling and film boiling. So all these things have been discussed in details, and one important terminology, that is the critical heat flux or burnout point, it is also discussed here. Okay, so these were in details the concept and the formation of the boiling heat transfer. So in the next lecture actually we will discuss the condensation heat transfer in details, and there we will see the different modes of condensation heat transfer, which are film and dropwise condensation, and we will discuss one derivation for laminar film condensation in case of a flat vertical plate. And based on those different formula we will also discuss some numerical in the next lecture. Okay, so this is the end for this lecture today.